Hello, this is 4.6, and this is part 3. This is example number 3, and when we read it, it says an open top cylinder can is said to have a volume of 250 centimeters cubed. The material for the bottom of the can costs 4 cents per centimeter squared. That for the curved side costs 2 cents centimeter squared. What dimensions will minimize the cost of the can? What is the minimum cost of the can? Okay, so if I look through the problem itself, I know I have volume, because it tells me a volume of a cylindrical can equals 250 centimeters cubed. And I also have things in terms of area. And I know it's area because we have 4 cents per centimeter squared and 2 cents per centimeter squared. So we're probably going to have to make a cost function dealing with the area, and we're also going to use the volume function. So just as a reminder, the volume of a cylinder can be found by taking pi r squared times h. Okay, so what does that look like? You know, if we have a cylinder here, we have the height, and then we have the radius r. So, and the area, remember the area of a circle is pi r squared. So you're basically taking the area of a circle, multiplying it by the height. That's how you get volume of a cylinder. So that's all fine and dandy. We notice we have two variables. Let's go ahead and look at the cost function. Okay, so I know I have 4 cents. That's the cost of the bottom of the open top cylindrical can. And I also know that 2 cents will take care of the side. Okay, so basically I have to add these together, and that will give me the total cost of the can. So let's deal with this. So C equals, the bottom of the can is 4 cents, so let's keep everything in cents. Let's leave that as 4. And the area of the bottom of the can is a circle. So the area of a circle is pi r squared. And once again, I'm using area because in the problem, it said 4 cents per centimeter squared. Okay? Plus 2. Now the side of the can, to find the surface area of that, I need to know what the circumference is and then multiply that times the height. So to find the circumference of a circle is 2 pi r, and then I'm going to multiply that times the height, and that will give me the surface area of the side of the can. Okay, so now that I have that, let's make this look a little bit prettier. So C equals 4 pi r squared plus 4 pi r h, and now I have everything in r's and I have an h. So what I can do is I can go forth and look at it, and I know that I can not rearrange the cost formula, because I don't know what the cost is, but I can rearrange our volume formula because the volume of the can is given as 250 centimeters cubed. So 250 equals pi r squared h. Now if I manipulate that equation, I can get h isolated to get 250 over pi r squared. So now that I have h isolated, I can take that h and place it in to my equation. So now I have the cost function, the cost of at r equals 4 pi r squared plus 4 pi r, and now instead of writing an h, I write down 250 over pi r squared. Okay, at this point, I'm going to do a little bit of simplification, because remember, whenever we are trying to find the maximum or minimum of anything, we're going to have to take the derivative of that. So the more you can, simplify before you start doing that, the better. So when I look at this, I can get rid of the pi and an r. So here's what I have left. Get the color back here. I have 4 pi r squared plus 4 times 250 gives me 1,000 over r. Okay, so that's my cost at r. All right, so if I want to write it again, before I take the derivative of it, I get 4 pi r squared plus 1,000 r to the negative 1. Now I am set to take that derivative. So let's go ahead and take the derivative of 4 pi r squared plus 1,000 r to the negative 1. Okay, so now I'm taking the derivative, so I'm letting you know I'm doing that. The derivative of 4 pi r squared is going to be 8 pi r. And the derivative of 1,000 r to the negative 1 is going to be negative 1,000 r to the negative 2. So now that I have my cost function as the derivative of that, my next step is going to be setting that equal to 0 and solving that. Okay, so let's go ahead and check this out. Notice that I have, this equation. Before I set this equal to 0, it actually looks like this, right? It would probably be wise for us to find a common denominator here. So if I find a common denominator, it's going to be r squared, because remember, I got to solve this, so I need a common denominator. So I had 8 pi r in the numerator. I'm adding r squared, so this is going to be r cubed. And then 1,000 over r squared is fine. So I can rewrite this as 8 pi r cubed minus 1,000 all over r squared. And that equals 0. Okay? Once again, I'm trying to solve for r. So, I can set the numerator equal to 0 and the denominator equal to 0. If I set the denominator equal to 0, r squared equals 0, r equals 0, well, that's a problem because, remember, it's a cost function. So this doesn't make sense. It'd be nice if the radius was 0, but we know that's not going to happen. Okay, so that doesn't make sense. So we're going to skip the denominator and look at the numerator then. The numerator says 8 pi r cubed minus 1,000 equals 0. So 8 pi r cubed equals 1,000. Now we're going to try to get r cubed by itself. So I'm going to divide both sides by 8 pi to get 1,000 over 8 pi. And now to get r isolated, I have to take the cube root of both sides. So let me make sure I put that little cubed in there. And then it's going to be the cube root of 1,000 over 8 pi. All right, so what is that? We don't know. We're trying to find the radius. So I would plug that into the calculator and get a decimal approximation. And when I do that, I get 3.4139. So I'm just going to round it off to 3.41. And that's my critical number, right? So my critical number is r equals 3.41. Okay, so at this point, I need to make sure that that's a minimum. So we're going to try a different approach with example 3 than we did with example 1 and 2. And what we're going to do is we're going to use a second derivative test. So if I find the second derivative of r, what I will do ultimately is plug in that critical point of 3.41 and see if my answer is positive or negative. Okay, so I'm looking for this just to let me know if it's a max or a min. And I can tell that because I'll either get an answer that's concave up or concave down. So just as a reminder, the derivative of c, if we go back to that, was 8 pi r minus 1,000 r to the negative 2. So the second derivative of this is now going to be 8 pi, and then the negative 2 is going to come down, so I'm going to get plus 2,000 r to the negative 3. Okay? So what I can write this up as, and once again, I'm just trying to rewrite it so it's easy to plug in. I get 8 pi plus 2,000 over r cubed. Okay? Now we take the critical number, which we know is 3.41, and we're going to plug it in for r. So plugging that into the second derivative, I get 8 pi plus 2,000, and I'm going to take 3.41, and I'm going to cube it. Okay, so basically when I do this, I'm really only interested to know if I have a positive value or a negative value. There are no negatives in this problem at all, so I know that my answer is going to be positive. So since it's positive, I know I have concave up. Okay, so when I have concave up, I know that that 3.41, where r equals 3.1, is the minimum. Okay, I hope that makes sense to you. All right, so now that I have that, I just need to know what the cost of the can is going to be. So now I'm going to plug r equals 3.41 into the original cost function. So the original cost function was 4 pi r squared plus 1,000 over r. That was the original problem. So now if I find the original problem at 3.41, I get 4 times pi times 3.41 squared plus 1,000 over 3.41. Okay? So crunching that number, I get 439.37, but remember, that's allowing cents, that's in cents, okay? So this is in cents. Now, if I want to change that to dollars, I just have to move the decimal 2 places to the left. So in dollars, the amount is going to be $4.39. That is the minimum cost that can will be. So that's how you do example number 3. We have 2 more left after this, so go ahead and watch the next one.